This is the second video on integration by substitution, where we're going to have a look at another little shortcut technique that you can use. We're going to do these examples, we're going to do them all the way through using the full integration by substitution technique, and then summarise it and try and spot what this pattern is, what the shortcut is at the end. So in this question here, the substitution I'm going to make is that u is equal to 3x squared plus 5. So when I differentiate that, I get 6x, and when I make dx the subject, I get du over 6x. Right, making my substitution now. Now the x, I'm going to leave that where it is, in fact, for the moment, because I can see that when I substitute my du over 6x instead of the dx, I can see that the x's are going to cancel out. So actually I don't need to replace this x, it's just going to be a 1 once it's been cancelled. The 3x squared plus 5, that's my u. My dx is now du over just 6, because the x that was there and there, that x has been cancelled out, it's gone. Now, this is a really easy integral to do. Take the 1/6 outside, 1 over u integrates to be ln u, and I've got the 1/6 at the front, and then just replace the u with my original substitution, which was 3x squared plus 5. And there we go, that's my answer to this question. Okay, next example. My substitution. And by the way, most of the time in your exams you'll be told the substitution that you need to use. However, it's good practice for you to get into spotting it for yourselves. In this case here, it's going to be the sign x that I'm going to replace, because if I can have e to the power u, it's a lot simpler. I know how that integrates. Differentiate this. When I differentiate cos, I get sine. When I differentiate sine, I get cos. Make dx the subject. Like that. Okay. Right, let's make our substitutions here. So, now this cos x, I'm noticing when I substitute this in, the cos x on the denominator here will cancel with the cos x here. And so I will just be left with e to the power u du. The cos x that I've had down here and the cos x I had here at the front, from here and here, they're cancelled out, they're gone, which is why the integration by substitution technique is so powerful. Because now I know this integrates to just be e to the power u, and I know that u is sine x. So there we go. Right, next example. I've got 6x times e to the x squared. The substitution I'm going to make is going to be u equals x squared. Because again, if I've got e to the power u, that's a lot easier. Differentiate that. Make dx the subject. Make my substitution. Right, I can see I've got a 6x here and a 2x on the denominator here. So those would cancel out. I'll just write them in there for now. But I know they're going to cancel out in a minute. And I'll just be left with the e to the power u du. So the 6x is there, my e to the power u, and my dx has been replaced with the du over 2x. This cancels with this and just leaves a 3 at the front, which I could then take outside the integral. And that is going to just leave me with 3e to the power x squared plus c. So, you might have spotted the pattern of each of these examples. You can see I've named this spotting a derivative. Because in each of these cases, you can actually do these questions pretty simply if you can spot at the beginning that there is a derivative involved. For example here, if you can spot that when you differentiate the sine function here, you get the cos function, then actually what you can do is just think, well, actually, let me just integrate this function, like the exponential function, like I normally would. And when you integrate the exponential function, you get the exponential function. So, just to check that then, if you differentiate this, well, differentiating the exponential function, I get the exponential function. But then I need to times that by the derivative of the inside function. So I times that by cos. And that does give you original function. So if you can spot that there's a derivative, it makes it a lot simpler. Again here, I notice when I differentiate the inside function here, I get 2x. And this is just 3 lots of 2x. So I could think, right, well, this is the same thing as 3 lots of 2x, like that. And then I know that this just integrates to be the e to the power x squared. Because I know that when I differentiate this, the e to the x squared becomes e to the x squared, but I times it by the 2x. And going back to that first example, again, I look here and I think, right, well, if I differentiate this, I would get 6x, which is kind of similar to the x on the top. In fact, I could think of that x on the top as being a 6x with a 1/6 at the front. That way, when I differentiate this, I do get what's on the numerator. And then I can think, right, well, that means this is just going to integrate to be the logarithm with the 1/6 at the front. So, whenever you are asked to integrate something where you have the derivative of the function multiplied by a function to some power maybe, that is just going to integrate to be the function to that new power of the n plus 1, integrating the power function like you normally would. Or if you've got the derivative of the function times the exponential of the function, that is then just going to integrate to be the exponential of that function. Or if we've got the derivative of a function over the original function, that is going to integrate to just be the logarithm of the function plus c. So if you can spot this derivative in each of these examples, then you can do these types of questions in a shorter, quicker way. However, I know some people find this difficult to spot, and it takes a lot of practice. So don't worry too much about it, really, because you can just do the integration by substitution technique, just like I did in the examples. Just do this technique. You can see it doesn't take too long anyway, but spotting the derivative can be a bit quicker for you.